Let's talk about what the James Webb Space Telescope has actually shown us about Betelgeuse, because the story that is unfolding is genuinely extraordinary. And it does not need to be exaggerated to be one of the most compelling things happening in astronomy right now. What Webb has revealed about this star over the past several years, combined with a series of stunning new discoveries in 2025 and 2026, has completely rewritten what we thought we understood about this ancient, unstable, deeply mysterious red supergiant sitting in the shoulder of Orion. And the science, the real science, is more fascinating than any dramatized version of it could be. Let's get into every layer of it. Let's start with the basics, because context matters enormously here. Betelgeuse is a red supergiant star located roughly 650 light-years from Earth in the constellation Orion. That distance makes it one of the closest candidate supernova stars to our own solar system. When you look up at Orion on a clear winter night and see that distinctively reddish point of light marking the hunter's right shoulder, you are looking at a star so large that if you replaced our sun with Betelgeuse and placed it at the center of our solar system, its outer atmosphere would extend somewhere between the orbits of Mars and Jupiter. It is, in the most literal sense, a stellar giant. And it is nearing the end of its life. Not imminently, not tomorrow, not in your lifetime in all probability, but on cosmic scales, it is in its final act. And what Webb has given us is the most detailed front row seat to that final act that science has ever produced. Now here is what makes this moment in astronomy so significant. For decades, Betelgeuse was one of the most closely watched and least understood stars in our sky. It is what astronomers call a semi-regular variable star, meaning its brightness shifts over time in patterns that are real but irregular. It oscillates in brightness on roughly a 416-day cycle tied to pulsations deep in its core. It has a longer cycle, running approximately 2,170 days. Scientists have debated for years what was driving that longer cycle. Was it convection patterns on the star's surface, magnetic activity, dust ejection, or something more dramatic, like the star burning through its final nuclear fuel reserves in the run-up to a supernova? The question mattered enormously because if that longer cycle was driven by late-stage nuclear burning, some models suggested Betelgeuse could be centuries away from collapse rather than hundreds of thousands of years away. Then came the Great Dimming. In late 2019 and running into early 2020, Betelgeuse suddenly faded dramatically. It dropped to roughly 40% of its normal brightness, falling from being one of the 10 brightest stars in the night sky to somewhere around 21st place. Astronomers worldwide were riveted. The public was captivated. The immediate question was the obvious one. Is this it? Is this the beginning of the end? Was Betelgeuse going supernova? The answer turned out to be no. What actually happened was that the star ejected a massive cloud of material from its surface, which then cooled and condensed into dust that temporarily blocked its light from our perspective. Not a sign of imminent collapse, a stellar sneeze of cosmic proportions. But the mystery of why Betelgeuse behaves the way it does, why it dims and brightens, why it ejects material at such dramatic rates, remained wide open. That is where the recent discoveries become genuinely transformative. In July 2025, NASA researchers announced a discovery that changed everything about how we understand Betelgeuse's behavior. Working with data from the Gemini North Telescope and its high-contrast imaging camera, along with nearly 8 years of observations from the Hubble Space Telescope, combined with data from the Fred Lawrence Whipple Observatory and the Roque de los Muchachos Observatory, a team confirmed something that had been theorized for nearly a century. Betelgeuse has a companion star. An orbiting stellar companion that nobody had been able to directly observe until now because the blazing light of Betelgeuse itself drowned it out completely. The companion was given a name honoring the Arabic roots of Betelgeuse itself, which means the hand of Al-Jawza, a female figure in Arabian legend. The researchers called the companion Sawarha, meaning her bracelet. And Sawarha, it turns out, has been the hidden explanation for some of Betelgeuse's most mysterious behavior all along. The companion star is racing through an orbit that takes it directly through Betelgeuse's extended outer atmosphere. As it moves through that plasma and gas, it carves a wake, exactly like the wake of a boat cutting through water. That wake creates swirling trails of dense gas that expand outward. And the gravitational and atmospheric disturbances it generates as it orbits are what have been driving the 2,170-day longer brightness cycle that astronomers had been puzzling over for decades. The 6-year pattern was never a countdown to nuclear collapse. It was the signature of an invisible companion stirring the atmosphere of a giant star. As the researchers put it, it is a bit like a boat moving through water. For the first time, we can see direct signs of this gas trail, confirming that Betelgeuse truly has a hidden companion shaping its appearance and behavior. And here is where the discovery becomes even more remarkable at the astrophysical level. If the 2,170-day cycle is explained by the companion's orbital influence, then the long-standing concern that Betelgeuse might be in the very late stages of carbon burning, just centuries from collapse, is significantly reduced. High-resolution imaging and long-term spectroscopy now indicate that Betelgeuse is more likely in a stable helium-burning phase, not its absolute final gasp, not a star hours or years from detonation. A star that is genuinely old and genuinely in its end stage by stellar standards, but one that most likely has hundreds of thousands of years ahead of it before the core finally gives out. The supernova will come. It is physically inevitable for a star of this mass, but the discovery of Siwarha shifted the expected timeline outward dramatically, from some models suggesting possible core collapse within centuries to estimates now running toward hundreds of thousands of years. But the story of Siwarha does not end with stability, because the companion is not going to orbit Betelgeuse indefinitely. Tidal interactions between the two stars are gradually pulling Siwarha inward. Astronomers calculate that the companion may actually be engulfed by Betelgeuse itself within approximately 10,000 years, long before Betelgeuse eventually goes supernova in its own right. What happens when a stellar companion gets absorbed into a red supergiant of this scale is genuinely unknown territory. Some researchers have speculated it could splash out significant quantities of gas, spin up the rotation of Betelgeuse, and potentially alter the properties of the eventual supernova itself. We may be watching, in the very slow motion of cosmic time, a stellar merger in progress. And, thanks to observations combining Hubble data, ground-based telescopes, and Webb's infrared precision, we are seeing the early signatures of that process. What has Webb specifically added to this picture? Webb's infrared vision cuts through dust in ways that no previous space telescope could match. It orbits the Sun, 1 to 5 million kilometers from Earth at the second Lagrange point, giving it a uniquely stable vantage point. Its 5-meter primary mirror, composed of 18 gold-coated hexagonal segments, collects light with a collecting area roughly 6 times greater than Hubble's. And crucially for studying objects like Betelgeuse, its instruments operate primarily in the near-infrared and mid-infrared portions of the electromagnetic spectrum, the exact wavelengths at which dust-enshrouded stellar atmospheres reveal their structure most clearly. When pointed at Betelgeuse, Webb can observe the outer layers of the star's atmosphere with unprecedented resolution, detecting streams of material ejecting from the surface, tracing how dust clouds form and cool as they drift away from the star, and mapping the thermal patterns and convective structures churning beneath the surface. Webb has observed massive convective cells generating turbulence on scales that dwarf anything in our solar system, detected plumes of hot gas moving outward at high speed, and tracked how the material ejected during the Great Dimming of 2019 continues to drift and cool through surrounding space years later. Because Betelgeuse is so large and relatively close by cosmic standards, its apparent disk is larger than almost any other star, making it uniquely suited for the surface-resolved imaging that Webb's instruments deliver at infrared wavelengths. And in the broader context of what Webb has taught us about stellar death and supernova progenitors, there's a separate but deeply related discovery published in the Astrophysical Journal Letters in late 2025 that deserves attention. Astronomers used Webb to identify, for the first time, a supernova progenitor star in another galaxy before it exploded. The supernova, designated SN 2025 PHT, appeared in the spiral galaxy NGC 1637 when its light reached Earth on June 29, 2025. Researchers turned to Webb's archival observations of that galaxy taken in 2024 before the explosion occurred and found a single bright red supergiant located exactly at the position where the supernova later appeared. This was the first time Webb had directly identified a supernova progenitor, meaning a star confirmed to be the source of a supernova. The star was so obscured by carbon-rich dust that it was completely invisible to the Hubble Space Telescope and optical light, but Webb's infrared sensitivity caught it clearly. Lid author Charlie Kilpatrick of Northwestern University described it this way: "We have been waiting for this to happen, for a supernova to explode in a galaxy that Webb had already observed. We combined Hubble and Webb datasets to completely characterize this star for the first time. The dust composition of that progenitor was itself a surprise. The team expected to find silicate-rich dust surrounding a dying red supergiant. Instead, Webb's analysis revealed carbon-rich dust, leading researchers to speculate that the star had dredged up carbon from its interior in the time shortly before it exploded. This discovery has profound implications for the long-standing problem in astronomy known as the case of the missing red supergiants, meaning the puzzling fact that the most massive stars expected to produce the most luminous supernovas are paradoxically the hardest to find in pre-explosion images. Webb's finding suggests the answer is dust. The most massive aging red supergiants are the dustiest, and that dust renders them effectively invisible to optical telescopes, while remaining clearly detectable at infrared wavelengths that only Webb can access from space with this level of sensitivity. What this means for our understanding of Betelgeuse is significant. Betelgeuse itself, already known to be surrounded by extensive dust from previous mass ejections, is the kind of star whose final approach to supernova might be partially or entirely hidden from traditional optical observation. If Betelgeuse were to enter its genuine final phase of collapse, the signatures might first emerge in the infrared, in precisely the wavelengths where Webb excels. This is why astronomers consider Webb not just a tool for studying distant cosmic history, but an essential instrument for monitoring nearby stars like Betelgeuse in real time. The telescope is not just looking back in time, it is watching the star next door. So where does this leave us on the fundamental question that everyone who has ever looked up at Orion eventually asks? Is Betelgeuse about to explode? The honest answer from the current state of the science is not imminently, not in any human-relevant time frame, and not in 2026, despite the excited headlines. No credible peer-reviewed study confirms a supernova happening soon. The discovery of Siwarha has actually extended the most plausible estimates outward. The evidence suggests Betelgeuse is in a stable helium-burning phase. Its dramatic behavior, the dimming, the pulsations, the mass ejections, the convective chaos visible at its surface, all of these are real, and all of them are evidence of a genuinely old and unstable star. But old and unstable by stellar standards still means hundreds of thousands of years by human standards. The supernova will come. And when it does, it will be spectacular. At 650 light-years, Betelgeuse is close enough that its supernova will outshine the full moon and remain visible during daylight hours for weeks or potentially months. And Earth is far enough away that there is no meaningful danger from the radiation and particle waves it will release. We will watch it, and it will be the most extraordinary thing any human eye has ever seen in the night sky. But here is the deeper thing that the James Webb Space Telescope has given us, beyond the specific data points about Betelgeuse's companion or the infrared signatures of its surface convection. What Webb has given us is the ability to catch stars like Betelgeuse in the act of revealing their secrets in real time. For the first time, we can identify the progenitor stars of supernovae before they explode. For the first time, we can map the dust and chemistry surrounding dying stars with the precision needed to understand what happens in those final stages. For the first time, we can directly detect the orbital wake of a companion star moving through a red supergiant's atmosphere and use that data to resolve century-old mysteries about the star's behavior. And looking forward, NASA's upcoming Nancy Grace Roman Space Telescope will add another dimension to this capability, with the resolution, sensitivity, and infrared wavelength coverage to not only see massive aging stars across nearby galaxies, but potentially catch their variability as they enter their final mass ejection phases. The cosmic equivalent of a star clearing its throat before the final word. The combination of Webb and Roman will give astronomers a monitoring system for stellar death that simply did not exist 5 years ago. When Betelgeuse does finally collapse, and it will, neutrino detectors around the world are already standing ready to catch the first burst of particles that would travel outward from the collapsing core faster than the light of the explosion itself, giving us a warning signal minutes before the visual fireworks begin. We will see it coming. We will be ready. And we will understand what we are seeing in a way that no generation before us could have imagined. Betelgeuse has not given us its final act yet. But Webb is ensuring that when it does, we will understand every note of it. That is the gift of this telescope to this generation of astronomers, and to anyone who has ever looked up at Orion and wondered what that red light is and what it will become. What do you think about this? Does the discovery of Siwarha change how you think about Betelgeuse's eventual supernova? And what do you believe Webb will reveal next about the stars closest to us? Let us know in the comments. Subscribe and turn on notifications because the universe is not done surprising us.